So did anyone do the mini exam? Want to turn that in? Okay. It was a fun one, right? Okay, that's right. He said he was going to have it. Anyone else? Okay, so last class we were talking about these change of variables, going from one variable to the other to try and make the problem easier to do. And I gave you the example of when we switched from Cartesian to polar, where that little r came from. And it was in this computation of this thing called the Jacobian determinant, this thing right here. So I've put that on the board over there. And we're going to do an example now that would be very similar to something you would see like on a test, like on the final or something. This is the type of problem you would see. And this is what the homework problems look like. So it says use the change of variables. So we have a double integral. Maybe we should start there. We have this double integral over this region D. We're trying to integrate 4x plus y with respect to area. So this is like a surface. And we're trying to integrate it. And we're trying to integrate it over this parallelogram that has these vertices. And so what we're going to do is we're going to take that region, D, and we're going to transform it into a new region in a different, instead of an xy plane, we're going to transform it into the uv plane. So we're somehow switching x over to something that's a function of u and v, and the y is going to be switched over to a function of u and v. And then from there, we're going to do the double integral. So let's see what this region looks like first. Okay, let's draw the region in the xy plane. Now let's see why we would even want to switch variables here, change variables. So if I plot this, let's see, -1, 3, here's -1, 1, 2, 3. I think I'm in a little more room here. That point right there is -1, 3, and then we have 1, -3. That's this point. And then we have 3, -1, which is this point, and then we have 1, 5, which puts us right here. So if we were to connect these together with straight lines, this is D. Okay, so we're supposed to integrate over this region. And do y'all see why that might be problematic? It's not a type 1. It's not a type 2. It's not a polar region, right? Now, we could split it up. We could probably go like, I don't want to draw too much on here. Let me see. Start getting messy. We could probably do this if we like split it here and looked at the right side. We would have an upper and lower function of x, and our x would go between something. So we could look at that as a type 1, and then the left-hand side, we could look at that as type 1. So it could be done, but the idea here is that if the region gets too complicated, maybe there's a change of variables that'll make it easier, all right? So really, this is more about the method than it is like, why don't we just do it the other way, all right? So how does this work out? So there's a lot of little little chores that need to be done, okay, at this point to make this region get switched over. So over here, I'm going to draw the UV plane. So we're changing our variables from x and y to u and v. So what does that what does this region look like when you map it over to that UV plane under this transformation? So all your x's become 1/4 of u plus v, and all your y's become 1/4 of v minus 3u. We need to see how that moves this over. Does that make sense? So that process, there's different ways you can do it. The book does it one way. I did it another way. You get to the same answer. I think I'm going to do it the way that would probably make most sense. I don't know. Let's first look at this thing and let's label some sides. So let's call this side 1. Let's go side 2, side 3, and side 4. I could have gone L1, L2, L3, F4. It doesn't matter. what I'm going to do is try and figure out what happens to this side right here if I just map every point on that line segment over here. Okay, where does it go? Does that make sense? Okay, so I need to look at S1. Now, in terms of x and y, can you tell me the equation of that line? Well, we have points, don't we? This is 3, 1, 3, sorry, no, that's not 3, 1. That's 1, negative 3, right? And this point here is negative 1, positive 3. So can you give me the equation of that line? I mean, we would have to grind it out, but we could, right? You have 2 points. You can find the equation of the line between them. Looks like the slope of this line is like down 1, 2, 3 over 1, down 1, 2, 3 over 1. So it's like down 3 over 1 or down 6 over 2. So negative 3 is the slope. Can you tell what the y-intercept is? It's supposed to be right there. 0. So that looks like that has the equation y equals negative 3x. Now you could have done this using that formula y minus y1 equals m times x minus x1. Right? You go calculate the slope, difference of the points, right? And then once you do that, you could use either one of the points and come up with the equation. I could do that, right? Okay, so I'm not going to go through the formal process of how I got this. I'm going to trust that you could do that. You would have to do that for each of these sides. Okay, so let me just, I did this before class, that way we wouldn't have to go through all that work, but are there any questions on what I'm doing at this point? I'm going to just get the equation of all those line segments. S1, this goes between, x is between negative 1 and 1. So to draw this line segment, I want to use that equation, but my x's are only going to go between negative 1 and 1. Agreed? Okay, now let me get S2. S2 is this one right here, and to save us some time, the equation of that line is y equals x plus 4. And what are my restrictions on x here? If I'm going to draw that line segment. Negative 1 to 1 again, looks like, right? Looks like 1, yes it is, because that's the coordinate of this point, is 1, 5. So negative 1 to 1. And then you have to get S3, which again, I've done the work on that. That should be y equals negative 3x plus 8. And that's going to be between x's, what, 1 to what? This is 3, negative 1, right? So between 1 and 3. And then finally, S4 was y equals x minus 4. And here x is between 1 and 3 again. Okay. So already this is quite a bit of work just to try and start to switch this thing over, right? Quite a bit of work. All right, so let's take a look at the transformations we're going to use. These are our transformations, right? I would like to know what this line becomes over there. So let's start with this one, S1. And I think I need to give myself a little more room. I'm going to make this smaller, and then I'm going to move it up. All right, so let's take a look at this. I'll draw that again in a second, because I'm just going to work on S1 right now. S1, I'm going to write down these equations. I have x is equal to 1/4 u plus v. That's one transformation. The other transformation is y is 1/4 of v minus 3u. Right? But if I'm on S1, I have this relationship, right? That y is equal to negative 3x. Right? So what I'm going to do is I'm going to replace this with negative 3x. So I have this equation, x equal, I'll just leave it. This one is negative 3x equals 1/4 v minus 3u. And then what I'm going to do is I'm going to solve this for x. Because if I solve this for x, then this is x, then they're equal to one another, aren't they? So if I solve this for x, I get, divide both sides by negative 3, I get negative 1/12 v minus 3u, like that. Make sense? Now equate these two together. 1/4 u plus v equals negative 1/12 v minus 3u. So you know how over here, this right here, this is an equation with y and x in it, and when you graph it, it's a line. Now I have an equation with just what two variables? U and v, so I should be able to graph this in the UV plane. Does that make sense?
What about the restrictions for x though?
We'll talk about the restrictions for x in a second. Let's get to this first, okay? So if I go and try and clean this up and make it a relationship between u and v that I can identify, really nice things are about to happen. So I'm going to multiply both sides by 12 to clear the fractions, all right? So multiply that by 12. You're going to get a 3 out here and then distribute it through. So you get 3u plus 3v equals, multiply that by 12 and you get a negative 1, and distribute that through, you get negative v plus 3u, right? Get that? Now, do you see what happens here? These u's cancel, and you get 3v equals negative v. So I'm going to move that v over, and you get 4v equals 0. And what's the only solution to that? V is 0, right? So v equals 0 is where that thing gets mapped over. Now what does v equals 0 look like in the UV plane? Let me put my UV plane here. This is my u and my v, right? If v is 0, then where am I? It's the u-axis, right? V equals 0 is the u-axis. So this line segment gets mapped over through this transformation just to the u-axis. Now the question would be, how long is it, right? Well, that you could get with your restrictions on x. But I'm not even going to need it. Watch. Let's just keep going. So this right here, that line segment is the transformation of S1, isn't it? That's the transformation of S1. So I'm going to call that transformation T. This is just notation the book uses, but that's just so you understand that if there is a transformation that's taking us from here to here, then this line segment is the image of that S1 passed through the transformation over to the UV plane. Got it? No questions? We've got to do that for S2, S3, S4. And then we'll see what this region looks like over here. Now, do you want me to go through the transformations for each one, or maybe just do one more? How about I do this one? Because this one and this one look different, don't they? Like that's different than this. But these are very similar to those two. Like this one has the same slope, right? This one has +8, this one doesn't. This one's +4, that one's -4. So I think if we do these two, then I can trust that you could do the next two on your own. Yes? Okay. So now, to do S2, I start with my transformations again. Or I start with, my transformations. Here they are. And now with S2, this is a little bit trickier, right? Because S2 is y equals x plus 4. So if you look at it this way, x would be y minus 4, right? I could solve this for x, just move the 4 over. So what I'll do is I'll come up here. I'm going to replace this y. Wait, what did I just do? Sorry, I wanted to solve for y, not x. Oops. It's already solved for x. Okay, it's going to be one of those days. Okay, this becomes x plus 4, right? That's x plus 4. And equals 1/4 and then v minus 3u, like that. Solve this for x, and then set them equal to one another again. So if I solve this for x, all I have to do is subtract 4 on both sides. And now equate them to one another. So 1/4 u plus v equals 1/4 v minus 3u, then minus 4. So what should I do now? we'll multiply everything by 4. How about that? We'll clear out those fractions, multiply that by 4, we get u plus v. Multiply that by 4, we get v minus 3u. Don't forget to multiply that by 4, minus 16. And then something good happens again, right? The v's this time cancel, right? And then let's move this over to the other side, and we get 4u equals negative 16, which means u is negative 4. And what does that look like over here? U is negative 4. Vertical line. This time, u is negative 4. 1, 2, 3, 4. Here's u is negative 4. And I have a vertical line like this. And that would be the transformation of S2. Make sense? And then we could continue and do this for the next 2 line segments. Okay? You all happy with that? Not happy. Are you okay with it? Or do you follow it? Yeah? Okay, let me tell you what the other 2 transformations become. S3, I believe, comes 8. Is v equals 8. Let me just double check it here. V equals 8. Yeah, S3, this one right here, becomes v is 8. 1, 2, 3, 4, 5, 6, 7, 8. Here's 8. And what I get is a horizontal line like this. So this is the transformation of S3. And then the last one is this 4th one here. See, I'm out of colors, I think. I'll just use black. So S4, what happens is it gets mapped over to U is 4. So that's your transformation of S4. Okay? So do you see the region of integration now? This parallelogram in the xy plane under that transformation gets moved over to that rectangle. All right? Isn't that nice? Because that right there, to do that double integral, right, to do this double integral, you will have to just integrate from negative 4 to 4 and then from 0 to 8. As opposed to here, we could have split it up, but then we would have like x is between constants, but y's are between 2 functions of x. So our limits of integration here would have variables in the limits of integration, where here they're going to be constants. And that's good, right? Wouldn't you say? Now, what no one has asked is, where did these come from, right? Like, why do that, right? Like, no.
Is there some way of taking our parallelogram and finding a specific?
Yes, there is a way, and maybe we'll address that right here when we finish it. Let's finish it, and then we'll see. Maybe we could have come up with those transformations on our own. In general, it's not super easy to come up with them, but the next example I'm going to give you, they don't give us the transformations. So we're going to come up with them ourselves. All right, so we're good here. I'm skipping half the work. Now we need to do the double integral. So what we want to do is, if we do this transformation, our new integral, let me just bring up the notes here so you can see it. I don't have to write it down on the board again. So if you have a double integral over d in terms of a function in terms of x and y with respect to area, what we have to do is switch it over to this new thing, s. So this is s for us. Okay, this is s. We're going to do double integral over s of our function, but we have to replace x with the things with u's in it. We have to replace the y with the things with the, u's and v's. We have to replace the y with the things in u's, with u's and v's. This is like in polar, where we had to go from x, switch it over to r cosine theta. Same thing here. We're switching our x over to something with u's and v's, our y with something u's and v's. This is the Jacobian determinant. In polar, that was r. But in this problem, what is it? We haven't calculated it. right? We need to calculate this Jacobian determinant for the transformation that we had. We still need to do this work. And then our integral will be with respect to u and v, okay? So we first had to figure out what the new region looks like. Then we have to figure out what the function transformed over is. And then we have to figure out the Jacobian determinant. And then we have a double integral we hopefully can deal with. All right, so let's do the Jacobian determinant. How about we do that next? So for the Jacobian determinant, let's again write down our transformations. They were x was 1/4. You'll have this written down. Was it u minus v? U minus v, and then it was plus here. And y equals 1/4 3u, right? Okay. So those are our transformations. So just realize this right here, we're saying that x is some function of u and v, and then here y is some function of u and v, right? That's what these are. So the Jacobian, I need to compute the determinant of this matrix. So that's where we go, you know, this, remember that thing? You go like this, these two multiplied, minus these two multiplied. That's where this comes from. Then we have to take the absolute value of it. All right, so let's do that. I'm going to be taking, so the Jacobian, I'm just going to call it J for Jacobian, is going to be, let's see, the partial of x with respect to u. So what is the partial of this with respect to u? Remember, that's just 1/4 u plus 1/4 v, and this one is 1/4 v minus 3/4 u, right? Distribute the constant through. So what's the partial derivative of this with respect to u? 1/4. Okay, now I'm going to do this partial of x with respect to v, which is also 1/4. And then the bottom left corner is the partial of y with respect to u, which would be careful here, negative 3/4. And then the partial of y with respect to v, which would be positive 1/4. Now calculate the determinant. I should actually be taking the magnitude of this thing. At the end, you have to take the absolute value. So now we go this times this, which is 1/16, minus this times this. What's that? Negative 3/16, which is, the end of the day here, 4/16, which is 1/4. And I don't really need the magnitude because it's positive to begin with, right? So when we did polar, right? When we did our polar transformation, we had to have that little r there. If we use this transformation, we are going to basically be scaling the entire answer by 1/4. It's almost like that this parallelogram, right, is going to be moved over to this rectangle, and everything has been scaled down by a factor of 1/4 when you did the transformation. All right? When you go from Cartesian to polar, the transformation does not squeeze down like a constant. It's a variable. It's r itself. It depends on r. Does that make sense? Okay. All right. Let's do the double integral. I think I'll bring the problem back up. Okay, let me erase all this because I don't need it. All right. Here we go. We're doing this right here. This now becomes the double integral. Okay. Let's do the limits of integration at the end. We are going to rewrite this function, but instead of 4 times x, it's going to be 4 times this thing, right? Which is just u plus v. That's beautiful. Okay, plus 8 times that, which means just distribute a 2 through, right? So 2v minus 6u. You'll see that? That's what we're integrating. Now what? We need the Jacobian now, 1/4. So why don't we just stick that 1/4 on the outside because it's a constant, right? So it can come all the way out. And then now we need the order of integration. Is it du dv or is it dv du, or does it matter? Does the order here matter? The limits are constant, so it doesn't matter. You just have to make sure you match them up. So I took the region off the board, but I know u went between -4 and 4, right? And so du will be on the outside. And then dv, that was my up and down. That went from 0 to 8. And also this right here, we simplify, it just becomes -5u plus 3v, right? Combining like terms. And would you agree that taking the antiderivative of this would be pretty clean? Right, antiderivative, and then all you do is take the antiderivative, then you'd replace v with 8 and v with 0, subtract, get an answer, then integrate with respect to u, replace u with 4 and subtract -4 plugged in, and pretty straightforward at this point. There's a lot of work to get there, but there it is. I'm not going to continue this. We'll get the answer though. While I'm typing this up, are there any questions on anything I did on that? I'm doing this just so you have an answer. Okay, so we have 1/4 out front. And we have -4 to 4, and then 0 to 8. And then we're doing -5u plus 3v. Yeah. Going with v first, then u. 192.
Did we have to take, find the boundaries for like the S1 and
The
S2?
x. No, I only did that just because it's a line segment. I just wanted to clarify, like y equals 3x. On S1, y equals 3x is the entire line. We're only looking for a little piece of it, right? So I just wanted to be clear, like x between -1 and whatever it was, 1, that gives us the segment. Now the region we got in the UV plane turned out to be a rectangle, right, like this. So there's really only one region it could have been. Like it has to map it to there. It couldn't have mapped it like there's no other region here that's closed. Everything is, couldn't be this, that goes forever. Does that kind of answer your question? Okay. All right, now, without getting too technical, I want to discuss something here. The transformation we have, right there, these transformations. I know a lot of you haven't taken linear algebra, right? Who's taken linear algebra? Anyone yet? No? You've taken it, or you're taking it? You've taken it? So this is what we call a linear transformation, all right? So you can tell it's a linear transformation because x is becoming something in terms of u and v, but these right here, like they're not squared, there's no square roots, it's not u times v, it's u plus v, right? And then of course there's some numbers in front, but it's linear, u to the first power, v to the first power. This is also linear. So the transformation that took us from that parallelogram over to that rectangle, because it's linear, we have a very special property, which is that lines go to lines. Anytime you go do a linear transformation, lines go to lines, all right? And points go to points. So if you would have known that to start the problem, you look at this and say, hey, that's a linear transformation, then what you could have done is just found out where those parallelogram corners got mapped to, and then draw lines between them. I want to show you that because it's much faster. All right, but it was worth it for us to go through the work mechanically to give you some idea of how you come up with them without because if it's a nonlinear transformation, what are you going to do, right? So going back to the parallelogram, we have the point, it was -1, 3. It was 1, -3, help me out here. 3, -1, 1, 5, right? Those were our points. So because this is a linear transformation, let me just try and figure out where the point, let's start with -1, 3, that point right there. Let's see where that goes. Under the transformation, what happens? So what we can do here is just go to our two transformations, replace x with what? Negative 1, and replace y with 3, and see what we get. Okay, so what happens here is we get negative 1 equals 1/4 times u plus v. And then this one right here, 3 equals 1/4 v minus 3u. We have two equations and two unknowns, right? Two equations and two unknowns. We can't set these equal to one another at this point because this isn't like, and previously it was like x and x, so we set them equal. So I'm just gonna start doing some algebra here. And then here, just multiplying both sides by 4 here. And then you either can solve that for u and plug it in here, or solve that for v and plug it in here, solve this for v, however you want to do it. Basically, we have a system of equations. It looks like this. U plus v equals negative 4, and negative 3u plus v equals 12, right? That's two equations, two unknowns. And then you can solve this. Make sense? I'm going to do it like this because I can work with this pretty easily right now. If I just go make that minus, make that plus, then I can do elimination, just add straight down. So if I add straight down here, what would I get? Negative 4u equals 16, so that means u is negative 4, right? Once I know what u is, I can go back and get v, right? And I can do that anywhere I want. Let me see. I could do it back here. If I know u is negative 4, then I move it to the other side. Just what would I get for v? 0. So v would be 0. So that means that when I go into my uv plane, right, I go to the point negative 4, 0. Negative 4, 0 is that point right there, right? So that point got mapped over to that. Make sense? And then you could continue to do this. Let's see, where would this point get mapped to? Let's not do the work, but let's think about it. Where did this line go to? This line went to the u-axis, right? So this would be the end of it, which would have been at positive 4, right? So that point would get mapped here. Yeah? And then these points would get mapped up to these, and then this is the important part. Once you have all 4 points mapped over, because it's linear transformation, lines go to lines, right? Lines go to lines, which means that these have to be connected with lines, which creates the box. Make sense? If it's nonlinear, you can't do this. Okay, if it's a nonlinear transformation, you cannot just get the points and then connect them with straight lines. So you know polar, is polar coordinates a linear transformation or no? No. No, it is not. Here's another way we could have looked at polar, just so you are clear with this. When you talk about polar, it's r cosine theta, right? And y is equal to r sine theta. And if we look at it more like in terms of u and v, you could say this is like u cosine v, and then this one is u sine v, right? Is it obvious to you that this is nonlinear? I mean, you've got, not only do you have multiplication between u and something that's not a constant, you have cosine of v. I mean, that's definitely nonlinear. So because it's nonlinear, when if you were to start with some polar region, right, and want to map it over to something here, you cannot just take these points and assume that the transformation is going to get you a box, because it's nonlinear. That's what happens. That's why we do polar conversions, but... Or do you know what? I should have said it this way. I shouldn't have said it that way. I'm sorry. Let me restate that. Because that region would go to a box. That's the whole reason we do it. I'm saying if you take an arbitrary region, let's do... let's take some arbitrary region. okay? And let's do a transformation over to UV using polar coordinates. You would get 4 points here, but there's no guarantee that what's connecting these is straight lines. You could have something like, you know, that, and who knows, something like that. And then this region would not be something you want to integrate, okay? So our conversions always want to be something that makes our life easier. Does that make sense? I feel like I'm confusing you. No? Makes sense? The only time you want to use polar is when your region of integration is polar. That's a polar region, right? That's a polar region. Under transformation of polar coordinates, that will go to some sort of rectangle. That will go to some sort of rectangle. Okay, let's move on. Oh wait, there was something else. Oh, how we were to get what we would use, right? Like how could we have determined what we might have got for our transformation here? Man, it's really, this one is difficult to see, but we'd have to go back to our parallelogram, which came from those points, and we would need to look at these. Y equals 3x. No, it was negative 3x. This one was y equals negative 3x plus 8, I believe. Y equals x plus 4. Y equals x minus 4. We'd still have to figure that out. Okay? And then what we would notice is this. These two are very similar, aren't they? Almost identical? So let me rewrite this one. Just tell me if you believe this. That's the same as y, x minus y equals negative 4. Right? So just move the variables to one side. I move the variables this way and move the 4 to the other side. And then that one would become what?
X plus y equals negative 4.
I bring the y to the right, so
X plus y equals 4.
wait, here, no, I'm moving the y to this side, I'm moving this 4 to this side. So that's okay? And then, what about the other two here? These are very similar, aren't they? I could write one of them as 3x plus y equals 0. I could write the other one as 3x plus 8 equals 0. Do you all see that? These two? Written that way? So watch. What if I let, what's that?
I don't see 3x plus 8 equals 0.
Yeah, why did no, that's not at all what I wanted. What did I want? 3x plus y equals 8. That's what I meant to do. Move this over. Leave the 8 there, right? So do you see this right here? X minus y is a constant. X minus y is a constant. 3x plus y is a constant. 3x plus y is 8. You'll see that? So here's what I'm going to do. I'm going to say, let's let u be equal to x minus y. And let's let v be equal to 3x plus y. Because if u is this, right? If u is this, then after the transformation, what is u going to become in the new place? U is going to become negative 4. What?
So we're positive 4?
Is one of them positive 4?
We have 2x minus y's.
Yes, which come from these two equations, right? So if I transform this over, right, if I say to everyone, hey everyone, I'm going to let u be x minus y, okay? Then after the transformation, this equation right here, which is really this, that would mean u equals negative 4, right? And then this equation right here, which really is this, in the transformation would become u is 4. Do y'all see that? And then this, if I let v be 3x plus y, then in the transformation it's going to become 0, and then it'll become 8. Do y'all see that? Okay? This still doesn't tell us how we got this, though. It tells me this is what I should use, right? This is what I should use. So what we do now is we take this and we solve it for x and we solve it for y. And we try and get it in terms of u and v. And so what I'm saying is this. let's solve this one. How do I want to do this? Let's solve this one for y, okay? Solve it for y, you get y equals v minus 3x, right? Okay, that's this one. Now go back up to this one. I'm just showing this to you because you asked, and so I'm showing you another way of doing it. So this becomes this. Now go up to this one. U equals x minus, now what's y? This right here, right? So v minus 3x. Now that equation has u, v, and x. So I'm going to solve it for x. U equals x minus v plus 3x, right? So let's get the x's together on the right side. Let's move the v over. And finally, let's divide by 4. And if we do that, we will have our first transformation. And then you do the same thing. You do the same process. Once, to get the y, you do the same thing. So it's a little messy, isn't it? But it can be done.
On our homework,
Yes.
given the transformation?
I believe the transformations are given on some of the problems, and then the others they aren't. But I'm going to give you an example right now of one that it's not. And let's just talk about it, okay? Let's just talk about what we're going to do here. It's real nice when they give you the transformations. Makes it easier to work with. So this says, what if you are given the transformation? The integrand itself might clue you into an appropriate transformation. And then I put here, linear transformations take lines to lines. So just remember that. So take a look at this one right here. Let's start by looking at the capital D, the region of integration. We are in the xy plane. We are at 1, 0. We are at 2, 0. We are at 0, negative 2. And we are at 0, negative 1. So we are looking at this trapezoid right here. And we are going to try and take that and do something with it. Now, again, you might be sitting there right now saying, no, I don't want to do all that work. I'm just going to split this up. I'm going to do a double integral over that, and then a double integral over that. Could you do that? Yes. And I think it would be easier, but can you integrate that? Are you feeling like you can integrate that with respect to x or y?
Yeah.
Could you?
Yeah.
Okay, let me ask you then. Let me do something to see if you really would feel comfortable with it. Let's try and integrate it with respect to y, which means x would be a constant, right? Right? So let me just challenge you with that. Let me just make x a constant real quick for you and integrate that with respect to y. If it were that, I would agree this is easy to do, but that's not what it is. How would you do that? Any ideas on how you would do that? I'm not quite sure I have an approach that I like in my mind right now. My first instinct is to do long division on this just to see what that really is. Right? And then once I get that, I might be able to use, split it up into separate integrals. I mean, not separate, different factors. But I'm not going to mess with it because I'm pretty sure we're not going to be able to get, well, you know what? Let's ask the computer.
What if you split it into e to the 5 over 5 minus y times e to the y over 5 minus y?
Well, I'm not sure. Is this what you mean?
Like 5 over 5 minus y, and then times e to the y over 5 minus y.
That.
Yeah. And then
You still have a problem here, though. I think you have a problem in both of them. By parts?
No, I'm just saying there's no, you don't know if it's 5 plus y, if you split it up like that.
Well, if you put these together, you would add these two, right? And they have the same denominator, so you'd have plus here, so it would become this. Algebraically, that's okay to go from here to here. The problem is, what now? Because you can't split this into two integrals. You got to keep them together. Look, let's just see what the computer does, because the computer is usually it's very telling. If the computer gives us some craziness as an answer, that means there's no way we were doing this, all right? Okay, so this is exponential of 5 plus y over 5 minus y. And we're integrating with respect to y. Oh, yeah, exponential integral error thing. Yeah, no. We're not doing that, okay? We are not doing that integral by hand. No way. The only hope we would have at this point, the only hope that we would have of doing this integral, I think, is to expand this out into a power series, and then we would get an approximation. That would be the best we could do. But as far as getting like the actual indefinite integral, the antiderivative of this in a closed form without doing a series, it's not happening, okay?
Sir, is it
Yes.
allowed? I don't think we ever went over this in Calc 2, like at least my teacher didn't. Like,
Uh-huh.
if you took like the ln of that and then had an e on the outside to like cancel it out, are you allowed to do something like that
You could do an ln and then an e.
on the outside?
The e would not be attached as a constant being multiplied. It's e raised to the natural log.
Yeah.
So you couldn't pull the e out because it's not being multiplied. Does that make sense?
Yes.
I know what you're,
Yeah.
well, I think you're saying this, like natural log here with an e, and then you pull the e out, and then that's going to go away. You can't
like
do that.
E raised to the integral. you're
Yeah,
gonna let it
can't do that.
Okay.
Yeah. All right, so have I somewhat convinced you that even though the region of integration looks approachable, that the integral itself doesn't seem like something we want to mess with? All right? So how about this? Well, I'm going to let you see if you can come up with what we might be able to use for, like you know, in the previous problem, I had put down here, like we had seen that x minus y had to be, I forgot what it was, 0, I think, and then x minus y had to be, no, it was -4 and then 4, right? And then I said, oh, maybe we should let u be x minus y. Can we just look at that and does anyone have an idea of just a guess as to what we could use? Like what we could make u and what we could make v?
I have a thought.
Just go for it.
So one of our variables, we can set equal to x plus y over x minus y to simplify the integral.
Okay, so you want u to be the whole thing.
Yes.
Okay.
So when we replace it through, we just get e to the u.
Yep.
Times.
Yeah,
whatever.
so I agree. If you do this substitution in here, right, then this becomes e to the u. And if you integrate that with respect to u, you're happy, aren't you?
Yes.
Okay.
Determine do it, but you could probably do that with like integration by part if you need to.
Okay, then what would v be?
V, you could probably choose V. You could probably use to simplify the trapezoid to a better shape. Possibly by using that technique you use where you find the equation of this. So we have two parallel lines here.
Yeah,
We could find the equations of them, and whatever are
like these two look parallel, don't they?
yes.
Yeah. So maybe we could find the equation that line, that would give us some indication, right? This might work. I'd be skeptical because I'm not quite sure what v would be in this. Like, what would you let your v transformation be?
Yeah, I can see what you mean.
What's that?
I would have done like e to the v over u or something like that.
Okay, so like use the numerator and denominator separately, as one of them is u and one of them is v. That would work too. if we do this, let's let that one, okay, and then v be what? Just x minus y, okay? Then wouldn't that new integral, the new integral would be, we'd be trying to integrate this. And if we integrate that with respect to u, v is a constant, right? So that would be easy to integrate. And if this were integrating with respect to v, we could bring v up, like v to the negative 1, and we should be able to handle that also. The problem is when the variable we're working with is both in the numerator and denominator at the same time. That's what was happening in there. You have the y's are both on the top and the bottom and the x's, so there's no easy way to go and integrate. Does that kind of make sense? This will work. Let's go with this, all right? So what I want you to see here is that even though it's not spelled out and we're not going to go and try and find parallel lines in a pattern, we're just going to go with the idea that if this were u and that were v, this would be doable for us. And let's see if we can gain anything out of this. So what do we do with this now?
Solve it for y and x.
We have to get it in terms of x and y. So we need x in terms of u and v. We need y in terms of u and v. So this is going to be our this is not our transformation, okay? This is what we're going to substitute. Our transformation is going to come from when we solve these for x and y. So what? I like this idea. I like adding. I like the idea of adding these two together. Am I allowed to do that? If x plus y equals u and x minus y equals v, can I just add straight down?
What would that give you?
What would it give me?
Yeah.
It would give me 2x
Equals u plus v.
equals u plus v, right?
Oh.
And then that would mean that x is 1/2 of u plus v. And that would be my first transformation. Does that make sense? I mean, you could get this, you could also get this by like solving this for x and then replacing it in here, and then, but I think that's faster. Do y'all see how quick that worked? Now, what else could I do? I'll keep that over here. I could have added them together,
You could have subtracted one of them.
or I could have subtracted or multiplied this by -1, something like that. Let me rewrite this. Let me just rewrite it first. But this time I'm going to multiply the top one by -1. That way my x's cancel. So -1 here makes that negative, right? So now add straight down, and what do you get? -2y equals -u plus v. And then divide both sides by -2. So y equals -1/2. That's dividing by -2. Then -u plus v. Like that.
Just to simplify it, you could distribute just the negative.
Yeah, I was going to do that actually, but I decided not to. We can do that. I was going to do it, but I was going to do it on the next step. So everyone okay with that part? And then the negative goes through. There we go. So there they are. Here are our transformations. We hope that by making those transformations, we will be in better shape, right? What now? Remember, this integral was impossible for us to do without this transformation. So what should I do now?
Substitute that in for x over.
I can substitute that in here. So this will be e to the u over v, but what do we still need?
Our range of integration.
We need our new region. We need to see what this thing under this transformation becomes, right? Right? So I'm going to do this with kind of the shorter approach. Are our transformations linear?
Yes.
Yes, which means lines go to lines, but it also means these points will be corners of a new, well, it's going to be a four-sided polygon, right? We're not guaranteed it's a rectangle. We're not, because we made the transformation ourselves and it may have not worked. By the way, the transformation that you had suggested in the beginning, right, that would have been nonlinear,
I realize. that
right?
there. Yeah,
So
after
we might have run into some trouble with the transformation over. But this transformation, because it's linear, should go pretty nice. So let's take these points and let's map them. Let me put our transformations up here. Y is equal to 1/2 u minus v. I like the approach. I mean, Don't get me wrong, I like what you did there. It was good insight, instinct there, but I just don't think it'll work. Also, I'm going to keep these up here because, well, do we really need them? Yeah, I'll keep them there. I'll keep them there.
You could use it to more easily find the 2 points,
If we know what?
X and Y.
Yeah, if we know our X and Y, we're going to be there, right? So I'll leave them on the board. I just didn't know if I left them there or if you had them in your notes, like what do you want? I'll leave them there. This point is the point, which one is this? 0, -1. This is the point 1, 0. This is the point 2, 0. This is the point 0, -2. So here we go. Let's see where this point goes. And I'm going to draw the UV plane right here. Here's U, here's V. So that point, 0, -1. 0 for X, -1 for Y. So where does 0, -1 get transformed into? So let's see what the U becomes. What does the U become? If I go 0, -1 here. U is -1. What does the V become? 0 and then minus -1, so that's 1, right? So it becomes the point -1, 1. Right there. Okay. Now let's just pick another one. 1, 0. See where that goes under the transformation. This is under our transformation T. So 1, 0 goes to what? 1, 1 again. 1, 1. And then let's go 2, 0. That goes to 2, 2, right? 2, 2. Which is, 2, 2. It's not a box. And then where does 0, -2 go? So 0 here, -2 is -2, and then 2, -2, 2. Which is, whoa, where is that? -2, 2. Wait a minute, we went from a trapezoid to a trapezoid, didn't we?
That's how they get you.
Yes.
Question. Do nonlinear, or
Trans-
in a linear transformation,
Uh-huh.
do parallel lines stay parallel?
Yes, because points go to points. So if these 2 points are parallel here, right, that means this line goes to a line and the 2 endpoints coincide. So these 2 lines are parallel, these 2 points will also be.
Okay.
Yeah.
And are angles always preserved as well? Because I don't see angles would.
Not necessarily. I think there can be a dilation.
Okay.
Okay, so we don't necessarily have the same angles.
All right, I'll probably look up later.
Yeah. Yes.
For this one, since it ended up just being another trapezoid, could you, okay, so since the second base is twice as large as the first one,
Mm-hmm.
if you like draw a parallel line from that first corner, like on the bottom right, to like the top, so then you have a rhombus, you can treat it like a square since it's the same length on all sides, and then have the triangle left over.
Oh, just do from here to here, and because that mapped over there would be.
Yeah, so like do the slanted line so it's like a rhombus, and
Uh-huh.
then since it's a rhombus, you can just treat it like a regular square, and then you have just the triangle left over.
I think again that's going to be depending, because you're integrating over this region, right?
Mm-hmm.
And so your region itself, like where you are within the region, dictates what this function is doing, right? So this is back to like that symmetry idea. You can't look at this as, oh, you know, if I move things around, it really just is a rectangle, because what's happening at that point is very different than what's happening, let's say, at this point. I may not be understanding your.
No, I think I see what you're saying. Yeah.
What do you think
I
he's?
understand what you're saying. I don't know.
What do you understand what he's saying
I
as being?
think